It is the iSAI-NLP section 12.
Good morning, my name is Ashira Sakashita Prasovete from Kazesat University Laboratory School, Center for Educational Research and Development. Today I will be presenting improved convolutional neural network-based blood pressure prediction from photoplethysmogram data to multi-window prediction averaging and interval classification.
The picture on the left is Dr. Apichat, who is my mentor for my JSTP project. The picture on the right is Dr. Anongnat, who is also my mentor, but for my school. This work is a part of JSTP program, supported by National Science and Technology Development Agency. The idea of this project came to me when I saw my grandmother feeling very uncomfortable while measuring her blood pressure. The machine needs to inflate a band tightly around her arm, which causes her a lot of discomfort. And also because in my junior high JSTP project, I work with photoplethysmogram or PPG signals for short to calculate the ground truth for heart rate estimates. This experience made me wonder if it might be possible to use PPG signal to measure blood pressure as well. After researching, I found that it is indeed possible, and here are the studies I will be referencing. This work by Scrumpf used PPG signal to predict blood pressure using AlexNet and LessNet model. The research also provides a clean 7-second PPG signal, along with the systolic and diastolic blood pressure for each 7-second segments. The PPG shows the blood flow changes as a waveform. As you can see here, when there's less blood, the higher the wave, and when there's more blood, the lower the wave. Systolic blood pressure is the blood pressure measured when the heart is beating, and diastolic blood pressure is a blood pressure measured when the heart is resting between heartbeats. The research also provided both the AlexNet and the LessNet model. The dataset is publicly available on the website. You can access it easily using this QR code. This dataset was also used in my work. This is the AlexNet model, and this is the LessNet model. The researchers were able to obtain a mean absolute error of about 12 to 15 mm mercury for SBP and 5 to 7 mm mercury for DBP. The LessNet model gave better results, so we chose the LessNet model for further study. My contribution to the research is to find ways to improve the accuracy of the predicted blood pressure. This work introduces two methods to improve the accuracy of the predicted blood pressure: a multi-window prediction strategy and a blood pressure interval classification model with mean regression. To use multi-window prediction approach, we need several data points associated with the same time duration. However, the 7-second PPG signals with matching time duration were not available. To overcome this, we came up with the idea of using the available data to implement the multi-window prediction approach, which involves creating 4 6-second PPG signal segments from 1 7-second PPG signals. We train the LessNet model using the created 6-second PPG segments with the randomly selected samples. We then test the model by predicting blood pressure 4 times, once for each of the 4 6-second PPG segments, all associated with the same time duration. The predicted blood pressure will be the average of 4 predictions, using both mean and median as an averaging method. I will go into further detail later in the slides. We create 4 overlapping 6-second PPG segments from a 7-second segment by shifting the signal by 41 samples, giving the sampling frequency of 125 Hz. This corresponds to a time shift of approximately 0.33 seconds. Then we train the ListNet model using the created 6-second PPG signal data. We split the 7-second data into 80-20 ratio, using the created 4 6-second PPG data associated with the 80% for training and 4 6-second data associated with a selected 20% for testing. For each 7-second data segments, 4 SBP and 4 DBP value will be predicted. We will then average the prediction to obtain a single DBP and a single SBP value. The table here shows an example of 4 predicted values and their average. We train the ListNet model with a 7-second data to be used as our baseline. When we made a single prediction with a 6-second data, the MAE was higher than the 7-second model. This means the prediction was less accurate, probably because the shorter duration provides less information for prediction, which lead to higher errors. However, when we use the mean and median prediction approach, we saw a reduction in MAE, which suggests an improvement in accuracy. For the classification model, we divide the blood pressure into 10 interval groups. Then the 10 interval groups can be arranged into 4 SBP and 4 DBP groups. For mean regression, the middle of each interval is assigned as a predicted value. The 10 interval groups and their arrangement will be explained in the next slide. Table 1 shows number of samples in each blood pressure interval. We select only the group with more than 50,000 samples. The group labels are shown in Table 2. As you can see here, SBP0 includes BP1 and BP0. SBP1 includes BP2, BP3, and BP4. SBP2 is so on and so on. DBP0 includes BP0 and BP2. DBP1 includes BP1, BP3, and BP5, and so on and so on. We used the ListNet 50 classification model from the reference research. It includes the convolution block and the identity block, as you can see here. We modified the output layer by replacing the two linear regression output for predicting the SBP and the DBP with these 10 classes. These 10 classes were derived from paired SBP and DBP intervals. The table here shows the confusion matrix for the 10 classes. From this 10 classes confusion matrix, we can also derive a confusion matrix specific for each SBP interval. For example, SBP0, which includes BP0 and BP1, the 72% value comes from the yellow box. We add them up, getting 144%, and since there are 2 BP groups, we divide them by 2, getting 72%. Similarly, the 71% here for the SBP1, we calculate it by adding all the light blue boxes together, which gives us 211%. And since SBP1 includes 3 BP groups, we need to divide it by 3, giving us 71%. For the DBP confusion matrix, the values are computed in the same way. For example, DBP0 includes both BP0 and BP2, shown in the yellow blocks. The 75% value comes from adding them up and dividing them by 2 because there are 2 BP groups, which gives us 75%. Other in this confusion matrix are calculated in the similar way. As I mentioned earlier, The mean regression assigned the middle value of each interval as a predicted BP value. The table here displays the predicted value corresponding to classes. For example, if a PPG signal is predicted as a SBP1, the SBP value of 108.75, which is the middle value between the 97.5 and 120, will be assigned as a predicted SBP value for that sample. The two-dimensional histogram showing the error of SBP and DBP are shown here. As you can see, the SBP error in each interval or classes values between -10 and 10 mm Mercury. This is because the SBP interval is about 20 mm Mercury, and we use the middle value of each interval as a predicted value. Similarly, the DBP error in each interval ranges between -5 and 5 mm Mercury. Each DBP interval is about 10 mm Mercury. If the blood pressure value were uniformly distributed, we would expect a mean absolute error of about 5 mm Mercury for SBP and 2.5 mm Mercury for DBP. However, look at this histogram. We can see that the blood pressure value were not uniformly distributed. They tend to concentrate at the edge of some intervals, which leads to a mean absolute error of 9.59 mm Mercury for SBP and 4.56 mm Mercury for DBP. Conclusion: using the multi-prediction approach, a slight reduction in mean absolute error were observed. The improvements were modest, but the results suggest that averaging prediction across multiple windows provides more reliable estimation of blood pressure. The findings suggest that if overlapping windows from longer signals were used, the multi-window prediction approach could lead to more accurate estimation. The blood pressure classification with mean regression approach achieves a lower mean absolute error and suggests that utilizing smaller intervals could yield even lower MAE values. This study was able to provide a practical approach for improving PPG-based blood pressure estimation accuracy.
Future works will consist of expanding the sample size to enable finer interval divisions, and providing more samples to train the regression model, and also applying the multi-window prediction averaging method into the interval classification. Thank you. Do you have any questions?
Thank you for your good presentation. And any question for the audience? Please.
Yeah, first of all, I really like your method that you use your averages. So could you talk about how fast your method is, if you have that?
This is just creating a model. It's not a real-time testing.
Oh, I see. Thank you.
Any question? I have another question. The first one, you choose the 4 or 6 seconds in training set. Why you do like this?
This one, right?
Yes, why you choose only the 4 and 4 to 6 seconds for training set?
6 seconds. The 6 seconds we chose because if it's less than that, there will be not much information for the less than 50 model to work with to predict the blood pressure. And the 4 is because if it's more than that, the shift here will be less, will be smaller shift, and it will be too close together. It won't be much difference between the first one and second one and third one.
Okay. Okay. Should be all question. Any questions or more questions? Okay, thank you.
Thank you.